Okay. Howdy, folks. Am I loud enough? Sure loud enough? Yeah, thank you. Okay, you all got my email that I sent you yesterday, right? And what I said was I am going to spend almost all the class today talking about polytomous and ordinal logistic regression. I want to say a few things about what we were doing last time, modeling strategy for several E's, but for the most part that's going to be covered in the lab tomorrow with some very good examples. But please be there because it's an important part of the course and relates to the midterm exam, as does what I'm going to cover today. I'm also going to talk very briefly today about another topic that's going to be talked about tomorrow in the lab. It has to do with screening variables. I'm going to say something a little bit about each, but primarily that's going to be talked about in the lab tomorrow. Okay? And if it turns out there is enough time on a week from today, which will be the week before the midterm, I may go back and talk a little bit more about some of the things I didn't say about several variables or about screening variables that maybe you'd like to hear about. So anyhow, so let's continue to talk about, let me say a few things about modeling strategy when there were more than two or more than one exposure variable. And you may or may not recall last time we looked at this this slide. I'm on the PowerPoint presentation that related to modeling strategy for several E's, and I had an example from the MRSA data where there were two exposure variables, right? Two exposure variables, E1 and E2, or previous hospitalization and PAMU. And then there were two control variables, age and gender. And I said, suppose at the first stage, the variable specification stage, this was our starting model. We talked a little bit about this starting model last time. And I said, if you remember, that when you have a model like this, when there's two or more exposure variables, two or more E's, you got sort of another complication in the modeling strategy because you have two different kinds of interaction terms. You have interaction terms of E's with V's or E's with W's, and then E's with C's, and then you have interaction terms of E's with E's, exposures with other exposures. So that means that there are some options about how you might deal with this problem. It's an extra nuance in dealing with several exposures. And there's more nuances. That's one reason why I'm not going to spend the whole class talking about all of this. But what I did do is I pointed out that based on that model where there were two exposures, that's a simple model because I could have had 10 exposures, but there were two different kinds of interaction terms. I showed you sort of the general form of this model very briefly, and then I said there may be some other ways to do this, but there are two alternatives that I talked about, how you would go about analyzing or going about the modeling strategy for dealing with this situation. And both of these alternatives, they started the same way, variable specification, and then they started the second step was involving the evaluating the interactions between the exposure variables and functions of the C variables. That would be EW variables. But the two alternatives differed in what the third step was. Alternative one said, well, maybe we ought to consider interaction before we consider anything else. So that said, if we're going to deal with the EWs, then the next thing we ought to deal with is the ECs. That's one approach. The other approach says, well, maybe once we consider the EWs, we ought to leave the E's until we deal with confounding and precision. And that's a different third step, which was dealing with confounding followed by precision. So those are the two alternative approaches. And what I did was I walked through, sort of walked through, how you would deal with both approaches in trying to analyze this model. And I walked through how you would, one step at a time, how you would go through that process, which I'm not going to do now, which might be reviewed to some extent tomorrow. Going to be reviewed in terms of some other examples, actually some realistic examples that the TAs will go through in the lab. So please be there. And then we eventually got to a point where, after I walked through this thing, we got to a point where, I'm skipping steps here, we got to a point where the model that we wound up with, and I made a few changes in the slides and mentioned that, and we were sort of on this slide right near the end of when we finished class on Thursday, and we sort of got to the point where once we were dealt with variable specification, interaction, confounding, we eventually got, and even interaction for both the EWs and the EEs, whether this was an example of alternative 2, we're down to a model which has 2 E's and 1 V, and the V was the result of having gone through confounding and decided to drop the other V that was eligible to be dropped, as in this case as a non-confounded, V1. So we're down to a model where there were 2 E's in the model. And then the question is, what I wrote here is, well, what do we do next? How do we deal with the E's? Well, again, that's what a good part of the lab tomorrow is going to be talking about. How do you deal with the E's? And there are a number of options on how to deal with the E's in this particular case. You do have a V2 in the model. You're going to keep that in the model because you've gotten to that point where you've decided it needs to stay in. But what do you do about the E's? Do you keep both of them? Do you drop one of them? Which one do you drop? Well, how do you deal with that? Okay, so again, that's something we're going to talk about a little bit more tomorrow. We're going to be talked about a little bit more, but this brings up sort of a more general question, which also going to be talked about tomorrow. What I'm talking about a little bit today is, what if it turns out you have a situation where the only variables you're dealing with are E's? You don't have any potential confounders. You've done sort of a literature and you're in this sort of hypothesis generating stage where you don't know anything about anything, and every variable you want to put in your model, as far as you're concerned, is a potential exposure variable. So if you're dealing with that situation, in a way, here's an example of it. Here's an example of that situation. There's no V's or W's in this model, they're all E's. So how do you deal with this? Well, maybe this is your starting model, the variable specification stage. The next stage after the starting model is what? In terms of the strategy we talked about. Interaction. That means we have to assess interaction. We only have one kind of interaction here because there are no V's. So there are no EW terms. So if we're assessing interaction, what we do is we deal with these product terms among the E's. And we might start off with a chunk test for whether any of the product terms are significant, and then we might do backward elimination to deal with the E's. Okay? But there's no V's over here. There's no EW, so we're not dealing with confounding in the sense. So once we get rid of or decide what we're going to do, whether we're going to keep any or all of these E's, the next step would be to decide whether we're going to deal with the EEs. The next step would be to decide whether we're going to deal with or drop any of the E's. So, for example, what I've done here is I've said, well, we deal with the EEs, and that's maybe, let's see, if I had already dropped, this was the model that I started off with. And then you're down to interaction assessment, confounding, but there's no confounding because you don't have any V's. So now then you're down to eventually dealing with the E's. And as an example of this situation, suppose after the interaction stage, I've got 2 models written down at the bottom of the screen. So suppose after this stage, the first of these models at the bottom of the screen is what you obtained after you started with a model with more product terms, with a lot more product terms. You wound up with only 2 product terms. If you had this model, what would that mean about what you would do next? If you knew that you needed to keep these 2, E1, E3, and E2, E3, what would that mean you'd have to keep in your model, in your final model? You'd have to keep E1, E2, and E3. But why not E4? Because that's not part of any product term you've decided to consider. So the process would be, okay, first consider interaction, and then maybe if there's any term you can drop, it's E4. Okay. Now, on the other hand, if it turned out when you assessed interaction, you find there was no interaction of any kind, and then that would mean that the model after interaction assessment involves the 4 E's. So any of these 4 E's can be dropped, right? Now, how do you do that? How do you do that? That's one of the questions. Again, it's going to be talked about tomorrow. One way to do that, to consider doing that, but there's several options, and that's going to be talked about tomorrow. One option is to simply you do a backward elimination with regard to the E's. You start with this model with these 4 E's in it, or maybe just this 1 E, and in this case, backward elimination would only involve E4. But let's focus on that. You start with backward elimination. You do backward elimination, see if you can drop any. And maybe the final model is just going to involve whatever's left after that. Now, there's some caveats to that, again, going to be talked about in the lab. There's a lot of nuances about this. Once you get into several E's, a lot of things are a little complicated to think about some of the different options that could happen. So eventually, you're going to be seeing several options. I'm just putting this slide up here just to show you what's going to be going over tomorrow. But there are several options. One option is you don't drop any of the E's. You just leave them all in there. And then you do something about trying to draw a conclusion about what it means with the E's. Another option is you start dropping some terms by backward elimination or whatever, but you got to be careful. So that's all I want to say about that. And again, as I keep saying, that'll be discussed more tomorrow. Now, another thing I want to talk about very briefly is, what we talked about tomorrow, is screening variables. Okay, so that's another PowerPoint presentation that I'm going to only very briefly talk about. Okay, and I just want to introduce this, and we'll talk about it in the lab tomorrow, and if I have time next Tuesday, I'll talk about it some more, depending on what your questions are. So here's the situation, is you're doing a study, you've done your literature review, you've identified a whole bunch of variables that you want to consider putting in your model. You've got maybe one or more E's and you have one or more C's. And I'm saying, what do you do when you have a large number of C variables and a model containing all these variables becomes unreliable, or even the model doesn't run? That happens. You sometimes decide, I'm going to put everything in the model, I'm going to run logistic regression, the model doesn't run. What do? Well, one of the things you consider doing is what's called screening. This is screening variables. It has to do with maybe getting rid of some of the variables before you even start. You started, you try to fit a model, it didn't run. So maybe one approach would be to let's get rid of some of them that we don't want to have. Okay. However, as I say down here, there are good ways and not so good ways to carry out screening. And again, that's going to be talked about primarily tomorrow, but I'm going to just say a few things about that. And I'm saying, so what do you do? Well, one approach to screening that a lot of people do, you may have done it if you've ever done any analysis before you even came into this course, is what you do is you have, let's say you have 50 variables, 50 C's, and you've got, let's say it's 1 E, and you've got 50 C's, okay? And what you do is you say, well, look, I'm going to look at each one of these 50 C's one at a time, and I'm going to see whether they're strongly predictive of the outcome variable. And I'm going to even ignore the E variable. I'm going to look as whether each one, I'm going to look at them one at a time, each one of those 50 C's are significantly predictive of the outcome variable. Is there an association between the C and the D variable for each of the 50 ones? So I get 50 test statistics, and I get 50 p-values. And what I decide to do is maybe I'll say the ones that are not significant, those are the variables I'll get rid of. So if I started off with 50 and 40 of them are not significant, I'll get rid of those 40 variables and I'll only be left with 10. That's a way of screening out variables. Get that? Get what I'm saying? Now there's a problem with doing that. The problem with doing that, and that's what I talk about, and that's what you're going to be talked about tomorrow. The problem with doing that is that if you screen out C's, using statistical testing, and the C's are potential confounders or potential effect modifiers, what aren't you doing correctly or potentially correctly? You're dropping variables that might be non-confounders, but you're using a statistical test to do it, right? What did we talk about assessing confounding? You don't do a statistical test for confounding. So here you're screening using a statistical test and dropping variables when you shouldn't. So how should you do that? Well, that's what's going to be talked about tomorrow. Another thing you're doing, or that you're not doing if you do this approach, 50 different tests, each C with each D, just those 50 tests and looking at those p-values. Another thing you're not doing is you're not looking at interaction at all of those C's. You're just looking at whether those C's are associated, predicted, but you're not looking at whether the C's interact with E. So that's another fault, another criticism of using this approach. So how do you do this approach? Again, that's going to be talked about tomorrow. Okay, I'm just trying to lead you into what it is, and that's something you need to think about, because in fact what a lot of people do, if you've ever done studies before or you've seen how, what a lot of people do is they do this approach. I often call this approach, where you just look at these statistical tests, a method zero. In the slideshow it's method zero, and method zero is questionable, but it's typically done by statisticians all the time. They do it all the time. If they're trying to drop variables, they just do these tests and they drop the ones that aren't significant. There's a problem with that. You're not looking at confounding or interaction. So I'm done with that as far as I'm concerned for now. So now what I want to do is start talking about the main topic or topics for today, and that has to do with polytomous and ordinal logistic regression. Let's see if I can find polytomous. And there it is. So there we are. So I took maybe even more time than I wanted, but we're going to talk about polytomous logistic regression now. Okay? So what's polytomous logistic regression? Okay? It has to do with the situation. Up until now, we've been talking about binary logistic regression, meaning there's only two possible, the outcome variable has only two possible choices, only two possible. You either have it or you don't have it. When you're talking about polytomous logistic regression, the outcome could have more than two categories. Not just two categories, it could have more than two categories. So polytomous, more than two categories. So that's what I'm going to do. I'm going to talk about it in terms of an application, in the context of an application of one of our former PhD students who did a study dealing with end-stage renal disease and did an analysis using polytomous logistic regression. So that's what we're going to do. The study is down here. In the logistic regression textbook, this book, chapter 12, which I hope maybe you've read by now, the logistic regression talks about polytomous logistic regression. In the textbook that you had last semester, by myself, Larry Cooper, Nizam Rosenberg, there's a chapter 23 in there, which actually talks about polytomous and ordinal logistic regression, and does it in the context, the polytomous one does it in the context of this Folkover study, a study that was done. You notice that I'm one of the authors of the paper that was published, because I worked with her on her study. But in any case, the example that I'm going to talk about is in the other book, the book that you had. So if you want to read about that, you go back to the other book. I assume you haven't gotten rid of it yet, or maybe you have sold it already because you're done with it, big mistake. No, I don't know. It's up to you. So let's talk about polytomous logistic regression. And first thing, again, up until this point in the course, or even in your previous course, you've learned about linear regression, when the outcome is sort of more or less a continuous variable, and that's a linear regression model. We've got several predictors. And then we've learned about binary logistic regression, where this is the binary logistic regression. Well, one way to write it, 1 over 1 plus e to the minus the linear sum, and it's predicting the probability of somebody getting an outcome where you can either get it or not get it. So that's the binary logistic regression model. Now we're going to talk about a situation where you can have more than two possible outcomes. And the simplest situation can be expressed by what's in this table. Okay, simple situation. You have an exposure variable. It's a simple situation. You have a single exposure variable, and you either have it or you don't have it. And you have an outcome variable, and the simple thing is you have an outcome variable with 3 categories, not 2 categories. So that's a simple extension of binary logistic regression. And a more general extension says, well, maybe instead of 3 categories of the outcome, you have 5 categories of the outcome. And not only do you maybe have an exposure variable, but you may have some other variables you want to control for. So it could be more general than that. So we're going to look at this to some extent and how to deal with this. Typically, when you have this situation, what you have to do is you have to decide, when you have more than 2 categories, one of those categories, and you're talking about polytomous logistic regression, one of those categories has to be considered a referent category. Just like even if it was an exposure variable and you had more than 2 categories, you usually consider one of those categories as an exposure, as a referent category. You do the same thing with the outcome. And so D0 represents the referent category. And I put it down here at the bottom to denote I'm comparing this category with D0 and D1 with D0, because D0 is the category we want to compare everything to. So now the example that I want to consider by talking about polytomous logistic regression is, again, it's a study of data obtained from end-stage renal disease on 3,000 or slightly more than 3,000 patients who have that illness and who were undergoing dialysis. And this is back a long time ago, 2002. Okay. And the question of interest of the outcome is what the cause of the illness was, the cause of the end-stage renal disease, and whether the cause was either hypertension, diabetes, or something else. Those are the 3 possible categories. Now, I've labeled hypertension 2, diabetes 1, and other disease 0. But if you look at those 3 numbers, 2, 1, and 0, does that really describe an ordering, a real ordering? Is hypertensive sort of higher than diabetes? Is more serious than diabetes? It's just a different disease. So these 3 categories are 3 categories that are not really ordered. If we're talking about ordered categories, then we're talking about a different kind of logistic regression generalization called ordinal logistic regression. But these are categories that really, even though I've numbered them 2, 1, and 0, they're really not orderable. You can't really say that hypertension is worse if you try to think about it. And the main exposure variable here of interest is race. Whether or not blacks are more likely than whites, whether that variable affects or is associated with the cause. Whether, if you're black, are you more likely to more likely to be hypertension than diabetes? That's sort of the question. But it's now 3 categories of the outcome. And then in addition to, this is the main exposure variable, this is the outcome, there are some variables to control for. So there are some C variables here. One of them is age when they started dialysis, and the other is whether they're male or female, their gender. Okay, so these are the 2 C variables. This is the E variable, and this is the D variable. The difference now is we've got 3 categories of it. Okay, the data set is obtained from a website that the original, the website for the 4th edition of the pink book that you had last semester, in the last spring. But that was the 4th edition, not the 5th edition, and the 5th edition website isn't up there. So it turns out that this data set is also provided in the data sets for homework for this course. But you don't have a homework assignment dealing with this data set. It's there. It's in that list of data sets in the subfolder of the homework folder on Blackboard, but just mentioning that. Okay. So anyhow, so again, one of the categories is usually designated a referent category. The choice of the referent category is arbitrary. And if you change it, you might change what the interpretation is because you're comparing different things to each other, but you're essentially going to get the same results, but you might change how you interpret the results. I'm going to make for the purpose of this discussion, I'm going to make the other reason for having ESRD, end-stage renal disease, that's going to be the referent category. And the other two categories, hypertension and diabetes, are the other two categories. So here's a table that describes this information. It's what I call the crude data layout for this situation. Why crude? Why is it the crude data layout? Because it has the disease outcomes, the illness outcome, it has the exposure status, but what doesn't it have? It's not controlling for anything, right? So this is the crude data layout, but it's not a 2x2 table. Now it's a 3x2 table, right? Because we have three categories of the outcome. So it's a 3x2 table, and you notice that in addition to that, on the very right-hand side, I've got these estimated odds ratios. So what are these odds ratios? See the 2.105? What's that, the odds ratio? How is that calculated? How do you think that's calculated? Well, odds ratios in a table, 2x2 table, AD over BC, right? That's the usual formula. What's AD over BC here? Well, we're comparing hypertension to other. That's one of the comparisons. And that's 630 times 395 divided by 323 times 366. This times that divided by this times that. And that's 2.105. So the odds ratio comparing hypertensive outcome to other outcome is 2.105. I'm not giving you whether it's significant or not. And the odds ratio comparing diabetes to other turns out to be 773 times 395 divided by 562 times 366, which is 1.484. And the 1 is just the odds ratio of that category with itself, which doesn't tell you anything, right? So, but what you see here is that you've got, instead of having one odds ratio in the crude table that you would get in the 2x2 table, you now have two odds ratios because you're comparing, you have a reference group and you got more than two categories. So if you had 5 categories, how many odds ratios would you get comparing to the reference group? 4, right? So you always have one less the number of categories of the outcome for the number of odds ratios that you're going to get. Okay, so what does this say? Well, without doing any statistical tests, it looks like there's a moderate effect of race on whether you've got on the cause of hypertension versus other, and not quite as strong, but not 1, but less than moderate effect in terms of the effect of race on the outcome diabetes compared to other. So you've now got two possible things to look at in terms of making a decision: is whether is race related to the outcome? Well, it looks like it is if we're talking about hypertension, not so much if we're talking about diabetes, but in some sense it's also sort of what you sometimes might call a dose response, but it's not dose. Why isn't it dose response? Because 012 is not ordering. There's no dose here. It looks like there's a difference whether you're comparing hypertension to other or diabetes to other. There's a difference in terms of the odds ratios of what they say. So what do you do with this? Well, let's talk about it. Well, one way to do this analysis, you just get this 2x2 table, you compute these odds ratios, you look at whether they're significant or not, these two odds ratios, you get a confidence interval around them, and you draw conclusions. No modeling. You don't have to do modeling, okay, if it's just a crude table. If you're controlling for a bunch of other variables, then you have to do modeling. But even if it's the crude table, you can even do modeling for it. Just like, remember we talked about logistic regression, binary logistic regression? If you had a crude table, there's a logistic model for binary logistic regression. If you only have two outcome categories, it just has the exposure and the outcome in there. It doesn't have any other variables you're controlling for. And when you run that model, you get a single odds ratio. Now you get Here you're getting two odds ratios, and there's a way to do this using a model. And here's the model. Here's what the model is. Now it's a little weird here, it's a little tricky, because the model has two components to it. The model for polytomous logistic regression has two components. Why do you think it has two components? The reason is if you go back to this, you're going to get two odds ratios. You know, because you've got three categories. So you have to have, it's not a single, it's not essentially one single model. There's a way to write it in a single way, but it's really got two components. One component relates to hypertension, or this is diabetes versus other, and this is hypertension versus other. And this says the log of this ratio of these two probabilities is a linear function of race, and the log of these two probabilities, but the numerator, the probability is different here, is also an alpha plus beta times race. Okay, that's what this is saying. There's two components to this thing. Now, first of all, I guess one question to ask is P of D equal to 1 given race divided by P of D equal to 0 given race, is that an odds? Is that an odds when you've got three categories? What's an odds when you've got three categories? Having it versus not having it, right? And this is not exactly that. It's like an odds, similar to it, but it's not an odds because it's only comparing one category versus another. It's like an odds. If you take the log of this, it's like a logit, but it's not a logit. It's not technically a logit. But that's okay when you're doing polytomous logistic regression. You're using logit-like models, logit-like way of describing the model. So now, what did we do when we're doing logistic regression, binary? If we had a model like this and I said, well, what's the odds ratio for the effective race? Just look at the first one. What would be the odds ratio? Race is a 0 1 variable. Just looking at the first component. E to the beta 1 1, right? E to that coefficient of the race variable. What would be the odds ratio dealing with the second model? Be e to the beta 2 1. So if for somehow you were able to get a program to run these two models, these two components, it's really a single model that has two components, and you got these estimates of these two betas and also these two alphas, you would ignore the alphas because that's what you typically do in any situation when you're trying to get an odds ratio. You ignore the intercept, and if you go e to the beta 1 1 and e to the beta 2 1, how many odds ratio are you going to get? How many odds are you going to get? Two of them. So, and it turns out that if you run this model using you can use proc logistic to run this model. It turns out that the two odds ratios you're going to get are going to be exactly these two, 2.105 and 1.484. So you can either do this without doing a model, and if you actually ran a model using a program and it turns out to be proc logistic, then you'll wind up getting exactly the same answers, 2.105 and 1.484, because this is a model that you're not controlling for anything. It's just the crude data. Okay, but now it turns out in this particular study, they want to control for some stuff. Okay, so what did they want to control for? Well, one variable was age. It turns out the way Natalia controlled for age was she considered age in 8 groups. So there were 7 dummy variables for age, and she wanted to control for gender. So the way to generalize these two component models when you have variables to control for is to write 2 component models, but now you're going to add to the models those variables you want to control for. Okay, so now this is the polytomous model when you're trying to control for age group and gender. Age group, 8 categories, 7 dummy variables. Now, if you were going to fit this model using a program, whatever it is, and you're going to say, okay, for this model, what's the formula for the effect of race on the outcome? In this case, it's diabetes versus other. What's the formula for the odds ratio for the effective race for this component? What's the formula? It's e to the beta 1 1, just like it was here. Is the e to the beta 1 for this model going to be the same as the e to the beta 1 for this model? Why not? Not likely, because now you're controlling for some variables, so it could change. Might not change. If it doesn't change, then you don't have confounding in a sense, right? But that's what it will be, and e to the beta 2, just like e to the beta 2, will be the odds ratio for the effective race in this component, but it might be different than e to the beta 2 in this model, because this model doesn't control for anything. So what Natalia did was she ran this model, or this model that has these two components, and fit this model and made it, got an odds ratio for the effect of each of the two categories of race. Each of the two different components for the effective race, and got these two odds ratios. Now let me ask you this question. For the crude data, suppose you wanted to test whether the race variable is significant in the crude data. What would be your null hypothesis? What's your null hypothesis about the question? I'm using this model, and I want to test whether race is significant, a significant predictor of this categorical outcome, which has three categories. How do we do that test? What's the null hypothesis? Beta 1 equals beta 2 equals 0, because the full model is what you see with the two components. And what's the reduced model? The reduced model will drop the two race terms out of the model, and it will just have the intercepts. Right? That's how you do it. What kind of a test did we call this? It's sort of a chunk test, because you're dealing with, more than one parameter. How do you do that test? How do you do that test? You fit the full model, which is this, and you fit the reduced model, which doesn't have the beta terms in there. And what do? You get these two minus 2 log L likelihood values, subtract one from the other, and it's a chi-square with how many degrees of freedom? 2. Why 2? Because you're testing two betas equal to 0. Okay? That's how you do it. How do you do that test? Is there an effective race in the model where you're controlling for age group and gender? There's no interaction terms. This model at the bottom of the screen is a no interaction model. How do you do that test? Again, you do a likelihood ratio test. What are the two models? Well, one model is what you see here with these two components. What's the reduced model? What's the reduced model? What does the reduced model have how is it different from this full model? There are two terms being dropped. What are they? This one and this one, right? But you're leaving these terms in there because you're still controlling for them. You're only testing whether race is significant in this model. Race taken together, given that you've got three categories. So how do you do that test? Again, it's a likelihood ratio test. How many degrees of freedom? Still 2, because what's your null hypothesis? Again, it's whether beta 1 equals beta 2 in with these two components. You're still testing whether two betas are equal to 0. So but the trouble now, or the difference now, is the likelihood ratio test for looking at for the effective race in this model is not necessarily going to be the same as the likelihood ratio test in this model, because this model is controlling for some variables. Okay, that's all I'm saying here. It's really not that bad. Now, in fact, that's what I've said. I've said if you're looking at the crude model, the full model is this. The reduced model only has the intercepts. The null hypothesis is that the two betas are equal to 0, and the likelihood ratio statistic will have 2 degrees of freedom. That's what I just said. Just showing it to you again. What I was talking about it now I'm showing it to you. How are we doing with this? Is this the worst thing in the world you've ever seen? It's not that bad. It's not that different. Okay? It's a little different. Okay? Now let me show you what happens when we actually do this analysis. I'll just show you some output. Okay? Now here's the output for the crude data. Here's the output for the crude data. Now you notice that you notice this is the model for the crude data. There's no other variables being controlled for, but how many parameters are there? There's 2 alphas and 2 betas, right? So in the output, when you run the model, and I'm not exactly telling you yet, but I will very soon, tell you how to run the model, how you do the actual computer work. But when you run this model, you're going to get an estimate of each one of these parameters. There's 2 alphas and 2 betas. So when you look at the output for the model that you're going to fit, you see this output down here? Intercept, intercept, race, race. There's 2 intercepts and 2 race values, right? Because that's what this model is, has 2 intercepts and 2 races, okay? And the 2 intercept values turn out to be their estimates, or these 2 values over here, and the 2 estimates of the betas are over here. Now it turns out that if you run proc logistic and you give it the right code, you'll get 2.105 and 1.484. Have you seen those numbers? Have you seen these numbers? These are the numbers I showed you at the get-go here, 2.105, 1.484. If I run this model with this data set on the 3,000 people, and I just have, I'm not controlling for anything else, I'm just using a 3x2 table, I'm going to get 2.105 and 1.484. This is the way I can run a model to get that, and I also get confidence intervals. And the formula 2.105 is e to the beta 2.1, and the formula 1.404 is e to the beta 1.1. Now, it usually turns out that when you get this listing of the 2 intercepts and the 2 races, it's usually the one that's on the top. It's usually the one for the higher category, the category that has the highest number. In this case, it's hypertension. So 2.105. But that's the analysis. Now, what about the test? Is race significant in this model? Where can you see that information? Where do you see that information on the screen here? Well, you don't see it here. You don't see it here. But you notice it says intercept only and then intercept and covariates, right? Now, if you notice, this is the model that has the intercept and covariates. And you see the 6091.865? That's minus 2 log L for this model, this crude model that considers the 2 race variables in the model. You see it says 6534.134 for intercept only? Well, that's the reduced model if you drop these 2 terms. So to get the likelihood ratio test, you look at these 2 numbers, you subtract one from the other, you get 442.269, 2 degrees of freedom, highly significant. So it says you got a highly significant effect of race. That's how you do that test. If you want to look at the individual odds ratios, you can always do that. But if you want to get an overall test of whether race, given the fact that you've got 3 categories of the outcome, this is the way you do it. Do an overall test. Questions? I'm not sure if you have any. It's just not that bad. Now, let me show you another thing. Now, again, if you're doing the model where you actually have the variables in the model, the control variables in the model, again, the full model has the control variables and the race variable in the model. The reduced model doesn't have the race variable in the model, but it has the control variables in the model. Right? That's the difference between the 2 models. Okay? The null hypothesis still has to do with the betas, because that's what you're testing, whether the race variable is significant. So it's still going to be a chi-square with 2 degrees of freedom, but it might not be exactly the same chi-square value, because the full and the reduced model aren't the same as what they were originally when you're dealing with the crude data. So you're going to get a different data set, a different computer output. So let's show you what happens here. Let's just see what happens here, at least part of it, and then we'll look at the other part. But now, if I test for race, I'm just talking about the test for race. You notice I have, when I run this model with the 2 components with all these variables that I'm controlling for, the intercept and covariate minus 2 log L, 6136.938, that's the minus 2 log L for this model. The model that has race and the 8 categories, 7 dummy variables for age and the gender variable. That's the minus 2 log L for this model. What do I have to compare it to? We have to compare it to a minus 2 log L for the reduced model, and the reduced model doesn't have race in it, right? That's the reduced model. Now, you notice in the output, you see 6534.134. Is that the minus 2 log L for the reduced model? And the reason why it's not is because it says intercept only. That's not the reduced model. The reduced model, in addition to the intercept, has these other 2 variables in there. So what you're going to have to do is you're going to have to run a second model, which doesn't have race, but has the other 2 variables you want to control, the other variables you want to control for. And it turns out when you run that, I'm just giving you the answer, it turns out instead of 6534, the reduced model gives you 6236.806. And so that's what you're comparing the 6136 to. So you subtract one from the other, and you get a 99.868, which is also highly significant. So what you get in the model where the investigator, Volkova, wanted to do, where she wanted to control for age and gender, you find that considering the outcome is in 3 categories and asking the question, is race a significant predictor of this outcome? The answer is yes, it's highly significant, because when we do this test, this chunk test, or this test with 2 degrees of freedom, we find out that it's significant. So that's how you do it. That's logistic regression for a polytomous situation. Now, in fact, look at this screen. What do you notice on this screen? What have I put up? Well, I got a heading. It says edited polytomous logistic regression output for the end-stage renal disease data evaluating the relationship between race and cause of ESRD controlling for age and gender, where age is grouped. So here's the output when I consider, this model. What do you notice about this output? How many intercept values do you get? Why? Because you got 2 components, one for each of the 2 component. You got 2 components here: diabetes versus other, and hypertension versus other. So you got 2 intercept values, you got 2 race values. In fact, you got 2 values for every variable for every other variable that's in the model. Because if you go look at this formula, now if you look at this formula a little carefully, you notice this says beta 1J and beta 2J. These are the components and beta 1,8 and beta 2,8. Why are these 2 numbers allowed to be different? Why are they allowed to be different? Because this is comparing diabetes versus other, and this is comparing hypertension versus other. So they could be different. You're allowing them to be different. So you're going to get 2 different estimates of the coefficient of gender, and you're going to get 2 different estimates for every one of these dummy variables, and that's why you get this mess over here. But in this mess, you might say, what do you really want to focus on in this mess? What's the goal of the study? Goal of the study is there effective race? So what information do you really want? Do you really want to focus on this stuff? Only if you're interested in assessing confounding, but if you just assume that you're going to keep those variables in the model and not assess confounding, the thing you want to focus on are the 2 race variables. And there it's coefficients, standard errors, and so on. Okay. Now let's look at the next slide over here. And this says edited polytomous logistic regression output evaluating control for, it's the same heading, but you notice on the top of this, underneath that, it says odds ratio estimates. So you see this 2.901? Where did that come from? Comes from exponentiating 1.0652, which is the coefficient of the race variable for one of the components. And if you exponentiate 0.5745, then you get 1.776. So those are the 2 odds ratios you get when you control for age and gender. Okay. When we ignored age and gender, we got 2.105 and 1.484. So we're getting different numbers. Why are we getting different numbers? Well, we're controlling for something we didn't originally control for. We're doing something that didn't change that much. Okay. In fact, you can see that, can you see whether, is the 2.901 significant? Can you tell whether it's significant or not? What makes you think it's significant? I've only shown you the confidence interval. Well, because the confidence interval doesn't contain the null value. What about the 1.776? That's also significant because it doesn't contain the null value, right? So I've got two significant odds ratios. It looks like there is a strong race effect. They're both significant, and I can get a confidence interval around each one. So I've just done polytomous logistic regression. That's all there is to it, more or less. Okay. Now, let's see what else. Whoa, what's this? This is the type of thing, wait a second, I thought it was easy. Okay. The general form of the polytomous logistic regression model that allows G, two or more categories of the outcome variable, and K predictors is given as follows. This is the general form of the model. Okay, that's what I've written over here. Now, if you think about this, all I've done was, you see G is the number of categories. If G is 3, what's G minus 1? 2, right? So that means you're going to have two versions of this model, just like we had here. Just like we had here. We had two versions of the model. If G is 3, you're going to get, this form is going to have two components to it. One will be for G equal to 1 versus 0, and the other will be for G equal to 2 equals 0, because G is 3, 3 minus 1 is 2. You don't go higher than 2. Okay? So that's the general form of the model. It's just a way of putting it together, but if you specify the G, you get each of the different components. If G is equal to 1, you have alpha 1 plus the sum of beta 1 G xj. If G is 2, you get alpha. So if capital G is 3, you're going to get two versions of this model. So that's the general formula for the model. Is this the worst thing you've ever? It's not that bad. You just have to think about it a little bit. But this is if G is equal to 3, you're getting these two models. G is equal to 5, how many models are you getting? How many components are you getting? 4. Because you have to have G equal to 1, 2, 3, and 4. When G is 5, 5 minus 1 is 4. Okay, so that's the general formula for the polytomous logistic regression model. As I said, so if G is equal to 3, G is equal to 1, 2, and if X1 is race and X2 is gender, making it simple, then the two models will look like this. If G is equal to 3, you'll get 2 models. If G is equal to 5, you'll get 4 models. That's all I've done here. Am I going too fast? No, I shouldn't be going too fast if you've read this stuff, but I don't know. Everybody's different. Okay, now, here's another thing. Whoa, wait, look, what's this? This is the formula for the odds ratio in the polytomous logistic regression model. Okay, it's the odds ratio formula. Okay, now, you notice it says ORG. See OR sub G? When we had 3 categories, how many odds ratios did we get? 2. When we had if we had 5 categories, how many odds ratios would we get? 4. Okay, so ORG, the G just stands for which one of the 2 or 3 or 4 odds ratios we're talking about, and this is the general formula for it. Now, if you think about it, a little bit, you notice that this part of the formula says XAJ minus XBJ. And the J is the jth X, whatever the X's are in the model. And A and B have to do with the two, if you're going to get an odds ratio, what do you have to do? You have to compare, remember X star versus X? You have to compare person X star versus X. In this case, I'm comparing person A with person B. So this is the X value for person A, and this is the X value for person B. That's the difference. I mean, it's just a little notational difference. Maybe I could have put an X star J and X without a star J. But I'm just saying the two different people are called person A and person B instead of person X star and person X. And that's the formula for the model. So let's look at that. So if G is equal to 3, just to make sure we got it, G is equal to 3, because that's what we were dealing with to start with. We just had these three categories of the outcome variable, the end-stage renal disease variable. So suppose we've got a model where person A is exposed and person B is not exposed. But person A has the same values on every other variable in the model as person B. That's what this says. X2, X2, XK, XK. Person A and B differ in only one way. One is exposed, the other is unexposed. Other than that, they're the same on all the other variables you're controlling for. You've got in the model. That means you're talking about controlling for these other variables. And if you actually crank things into this formula, OR1 will be E to the beta. It's an E to the beta formula. Will be E to the sum, I goes from 1 to K, beta 1J XAJ minus XBJ. But you notice that X2 and X2 are the same for person A and B, for persons A and B. So when you're talking about the second of these J's, this part drops out of the model. Everything's going to drop out of the model except for the very first value of the first variable, and all you're going to get is e to the beta 1 and e to the beta 1, 1 and e to the beta 2, 1. So this is the general formula for the odds ratio in a Polytomous logistic regression model, and this is what you get. This is what the two odds ratios will look like if you use this formula by plugging in what you've got. And it's really not really different than what we did when it was binary logistic regression, except now we've got two odds ratios instead of one odds ratio, or four odds ratios if there were 5 different categories. So that's Polytomous logistic regression. That's the odds ratio general formula, and that's the model, the general formula. Now, how do you do this in practice? Well, here's the code. Here's the code. How do you do this? You have a data set, this end-stage renal disease data set. Okay. Now, I've got 2 sets of codes written on this slide. What's the difference between what's here and what's here? What's the first one? What's the first code doing? Can you tell me what it's doing? It's the crude. It's the analysis of the data. The outcome variable is CERSD, C for categorical, ESRD. And so that's what the outcome variable is. Okay. And it's got 3 categories, 0, 1, 2. Okay. It's got race, and that's the only variable in the model. There's no other variable in the model, no other predictive variable in the model, so it's the crude. It's race on the outcome. Okay. Now, the difference between what's written here and what's written when you're doing binary logistic regression is this extra option, link equal to G logit. That's the key thing you have to write if you want to do Polytomous logistic regression. You say slash link equal to G logit, and that tells Proc Logistic to do a Polytomous logistic regression and get all the output I showed you before. What's the difference between what's here and what's here? What's the difference between what's here and what's here? The difference now is I'm now controlling for age and gender. You notice I've got age G, but you see this statement, class age G? What have I done here? There's a variable called age group, age G. It takes on 8 values, but I've defined it as a class variable. So what is it doing? It's defining 7 dummy variables because I've used it. So this is the model that I'd be using if I wanted to do that model that controls for age and gender. What if I wanted to consider interaction between race and gender? What would I have to do? How would I change what I've written over here if I want to just consider the interaction and I wanted to control for age and gender and also have race? What would I have to do? I'd have to add something to the model. What would I add? A race times gender term to this list, right? race, age, gender, race times gender. And then I'd have to consider a more complicated e to the beta plus delta form for the odds ratio. Other than that, it's the same. Okay? So if I remember correctly, if I go like this, yeah, that's what I thought. I'm done with Polytomous Logistic Regression. That's all it is. Okay? Did you get it? I'm not sure. But it's really, this is how you do it. What? You're not sure. You know, you're not going to be sure until you read it over, look at this, but that, all it is, again, if you're doing Polytomous Logistic Regression, instead of having a single component for your model, you have as many, wherever it is, you have as many components as you have one less the number of categories you're dealing with. And then the output's going to look worse. I mean, here's the output. It looks worse because you're going to have 2 intercepts and 2 races and stuff like two race coefficients. But that's the reason why you're getting that is because you're getting odds ratios comparing one category with a reference group and then the other category with a reference group. That's what you're doing when you're doing Polytomous Logistic Regression. So it's not as bad, but some of you might think this is the worst thing that ever happened. Not yet, because I haven't started talking about Ordinal Logistic Regression, which I'm now going to start to do. Okay, so here we go. Ordinal Logistic Regression. Okay. Okay, let's go. Ordinal Logistic Regression. Boom. Okay. This is easier and not easier. How can that be? Well, let's see. By the way, how do you pronounce this? I never pronounce it well. Acinetobacter? Acinetobacter. That's right? Acinetobacter? Acinetobacter. Okay, and I'm just going to say the A variable. Acineto, because I always screw it up. Okay? So now I want to explain some things. Okay? But that's the study. Okay? I'm going to talk about. Now, ordinal logistic regression is an extension of standard binary logistic model to allow ordinal outcome variables. The categories of the outcome variable have a natural ordering. Now, those 3 categories we had in the Polytomous, hypertension, diabetes, other, didn't have a natural ordering. You couldn't necessarily say one was worse than the other, or higher, or more severe, or whatever. They were different. Okay, so you have to have an ordering in order to do this. And the advantage of doing ordinal logistic regression when you have an ordering is that somehow in the analysis you're making use of the ordering to get a little bit more of an efficient analysis of what's going on. You're making use of the ordering in terms of how you're doing the analysis. Now, there are several different ways to do ordinal logistic regression, and the most popular form is called the proportional odds or cumulative logit model. 2 different ways. The proportional odds model is what I'm going to primarily talk about, the PO, the proportional odds model. Okay. And there are other types of logistic regression models to consider if the assumptions for the proportional odds model are not satisfied. And there's a paper that I reference over here, and it's on this list of papers. Not on this. It's on somewhere. There's a list of papers. But let's go back to this. So there are other types. Now, the thing is if you want to use SAS to do ordinal logistic regression, the only thing that SAS allows you to use is the proportional odds model. That's the only thing that's in SAS right now. There are these other methods. If you want to use these other methods, then you're going to have to look them up and figure them out or something and find a program that does it and, you know, get a reference and look at the computer program that did it. So it's more complicated to do something else. Now, that doesn't mean that because it's harder to find these other things that you should just, if you got an ordinal outcome, you should just use the proportional odds model. Why doesn't it automatically mean that you should use the proportional odds every time you have ordered outcomes? Because there's an assumption that has to be satisfied when you're using, and it's called the proportional odds assumption. That has to be satisfied. If it's not satisfied, you shouldn't use this model. Okay? What are your other choices? Well, there are some of these other choices that I saw, other types, And there's another choice that we've already just talked about. What's the other choice? What's the other choice that you could use if you decide, I want to use the ordinal, the proportional odds model, but it's not satisfied. I can't satisfy the assumption. Well, maybe just use Polytomous. Okay? Now, if you use Polytomous, you're not getting as good a deal as you might get if you use the ordinal model, the ordinal Polytomous proportional odds model. But if you find that that assumption is not satisfied, you are getting a better deal because you can't use the proportional odds. It's not satisfied. The assumption is not satisfied. So Polytomous is an option. There are better options, but it's an option if it's not satisfied. Okay, so let's and these are the different. You see, I got a star over here. The reason I got this star is because that's the one that's in SAS. And it's in Logistic. You can use Logistic to do this. Okay? And there are these other options that are more complicated. Okay? Which I'm not going to get into. Where you have to read the paper by, well, the paper on this list, Ananth and Kleinbaum. I don't know who that Kleinbaum guy is, but, you know. Anyhow. Now, let me just say a little bit more about ordinal regression models. Ordinal variables, when we talk about an ordinal variable, again, it has a natural ordering. Here are some examples of an outcome that's ordinal. Cancer tumor grade. Maybe that's your outcome, ranging from well-differentiated to moderately differentiated to poorly differentiated tumors. That's ordered. If that's your outcome, maybe you want to consider doing ordinal logistic regression, as long as this proportional odds assumption is satisfied. Length of inpatient hospital stay. Length of stay. Short, medium, long. Short, medium, intermediate, long. That's ordinal, right? Time since previous mammography. That's the example that's in the chapter that's in in the Logistic Regression book, chapter 12. Time since previous mammography, ranging from never, within 1 year, greater than 1 year. That's ordinal. Okay? So if either one of these things are your outcome, you might want to do Polytomous, ordinal logistic regression, but as I say here, you can always model using Polytomous logistic regression, but you're not getting the extra stuff you get in terms of efficiency and stuff, statistical stuff that you get when you use ordinal. Something else you don't get, but I won't be talking about that until next time. Now, let's talk about this example. Acinetobacter. See, I'm terrible, right? Did I get it? Acinetobacter. Okay, that's the problem. Okay, and if people have this bacteria, they can be resistant to treating it. Okay, so it has to do with people who are resistant to being treated to this bacteria. Okay, and that's what all this says. Okay, now there was this paper that I'm referring to, and it was done by a person with a very interesting name. Rebecca Sonnenschein, as opposed to Moonenshine or something, Sonnenschein. I don't know if she ever changed her name, but when I first started working with one of the divisions I'm still working for, and I started working there, she was an EIS officer and she had this problem, this issue, and I spent a lot of time working with her on this thing, so I got to know Rebecca Sonnenschein. Okay, and this is a retrospective matched pair cohort study. Wow, what's that? It's matched. It's matched, and it's a cohort study. It's not a matched case control study. It's a matched cohort study. So I got to describe it a little bit. Okay, it uses patient records in a period in the early 2000s from 2 tertiary care hospitals in Baltimore. The data came from The Wire. No, I'm just kidding. Investigated the impact. I'm having trouble wanting to watch The Wire because every other word is 4-letter word on that. So it's tough, to deal with that. I know those words, but okay. And anyhow, this study investigated the impact of multi-drug resistant Acinetobacter infection status on 3 outcomes. There were 3 outcomes. In-hospital mortality. One outcome was whether the person died or not. Binary. Well, that's not Polytomous or ordinal logistic. No, it's length of hospital stay. That's the focus I'm going to talk about. Now, length of hospital stay is a continuous variable. You know, you measure how long were they in there. Okay, so I need to talk a little bit more about it. Length of stay in an ICDU, well, that's another variable like that. But the one I'm going to focus on is length of hospital stay. The exposure status, the exposure variable, there were three groups of exposure variables. One was patients who were resistant to treatment. Patients with MDR, Acinetobacter infection. Okay? And there were two other groups, but one of the groups we're going to ignore. We're really only going to focus on this other unexposed group, patients with susceptible Acinetobacter infection. Susceptible Acinetobacter infection means that they're not resistant. They could be treated for this infection and maybe get better. Okay, that's what the second. So we're comparing exposed to susceptible. So there's two categories of exposure. That's what I say here. Okay. Now, so the exposure variable is 1 of exposed, 0 of unexposed. And exposed were resistant, the unexposed were susceptible. The outcome variable, see where it says ordinal hospital days, ORD hospital days, defined from terciles of hospital length stay. That's going to be the outcome variable, length of stay in the hospital. Ordinal outcome variable, using the following three categories. 0, hospital days between 0 and 9. 1, if greater than 9, but less than or equal to 23. And 2, if the hospital days were greater than 23. Is this an ordinal outcome? Yeah. It's short, medium, and long. Or, you know, that's what it is, right? So this is an ordinal outcome. Okay. Now, first thing to say is, you know, this hospital days is continuous variable. So why didn't we just do linear regression? Well, it turns out that when we tried, Rebecca, whatever, tried to do linear regression, she found that this variable, hospital days, wasn't normal, wasn't normally distributed. She tried to transform it, it still wasn't normally distributed. So then we said, well, what other way can we do it? We said, well, let's not do a continuous model. Let's take this variable and put it into categories. And we defined these ordinal categories. That's why it was done that way. Okay? So that's the variable ordinal hospital days. Now, remember I said there was matching. Okay, so let me explain the matching. Okay. Started with the exposure time prior to infection, where a susceptible referent patient, I have to explain this, had to have a pre-infection length of stay within 5% of the matched resistant patient's pre-infection hospital length of stay. So there's people who were resistant, people who were susceptible, and a susceptible person had to have about the same length of time prior to getting infected, the same amount of hospital time, had to have the same pre-infection length of stay as the resistant person. That's how they were sort of matched, to be similar in how long they were in the hospital. Okay, so that was this variable X time, or exposure time. But we actually decided to use a variable called mu X time. Now this is going to get you a little bit. Remember when we talked about matching? We talked about matching. We said when you match in a case control study, we said how did you do the analysis? You did conditional logistic regression. Remember that? And you had to do that when the number of matching strata were large. Okay, and the problem is, if you're using proc logistic and the number of matching strata are large, and you've got a cohort study, you can't do it. You can't do ordinal logistic in a cohort study. So we had to figure out some way to do ordinal logistic without, you can't do it with matching. So what we did is we said, well, let's now, instead of having a whole bunch of different matching strata that were large, we're only going to, you see where it says, we define this variable 0, 1, 2, 3, 4, 5, 6, or 7. There's only 7 matching groups. It's like pooling. It's like we did pooling. Only 7. If the number of matching strata is small, then you don't have to use conditional logistic regression. That's what Eli talked about way back when. And that's what we did over here. That's what we did. We had a small number of matching strategy. So we didn't have to do conditional. And then there were two other variables, Apache and Charlson. Apache is not an Indian, a measure of severity of illness prior to the infection, and Charlson was a summary of comorbidities. So there was an exposure variable of interest, the outcome, this ordinal outcome of length of stay. There's this matching variable, and there's two other variables being controlled for that weren't matched on. Okay, and it's a cohort study. Okay, and here's some data. Look at this data. Now, in this case, I'm not even talking about the other variables. I'm watching the clock because we have to finish in a minute or two here. But I'm looking at this. Now, you see, this is a 3x2 table, right? It's a 3x2 table. Okay? And it's got 210 and infected susceptible. So that's the data that we have. 3 categories of the outcome, and it's the crude data. These data do not control for matching or for the other variables. An ordinal logistic model allows for control of the above variables. Now, look at this is the last thing I'm going to do. Look at this slide. This slide. Okay. Now, I've taken this table and I've divided it into 2 subtables. Okay. I've done it in a weird way. How did I get this table from this table? See, it says 40 and 36. Where do I get the 40 and 36? 24 and 16 are 40. 13 and 23, 36, right? And then I've left the last row here. So what I've done is combined 1 and 2 and compared it to 0. Isn't that what I've done? 1 and 2 combined compared to 0 is what this table is. What's this table? It's 2, because that's 2, 24 and 13, and I've combined 0 and 1, 32 and 43. That's what I've done to get these 2 tables. Notice what I haven't done is I haven't combined 0 and 2 and compared it to 1. I didn't combine 0 and 2 and compared it to 1. Why didn't I do that? Because that messes up the ordering. If I go 0 and 2 versus 1, that's not allowed. I can only keep the ordering if I want to do this. Now, if I look at these 2 tables and I compute the odds ratio for these 2 tables, that's what they are, 1.39 and 2.48. And I said these 2 odds ratios should be approximately equal to justify using the ordinal logistic regression model with a proportional odds model. Are they approximately equal? They're terribly not equal, right? Okay. So it looks like if I wanted to do this analysis with the crude data, I couldn't do the proportional odds model. I'd have to do something else, like Polytomous or something like that. But we'll continue this next time. It turns out that if we think about the variables we wanted to control for, we could still do the proportional odds model, because we'll see that. Okay? And that's going to be the subject of Thursday's class. We're going to finish up ordinal logistic regression model. We're going to start with this. Okay? So, happy holiday. Happy holiday. What holiday? Is there a holiday coming up? Some people are celebrating a holiday. Not everybody. I'm one of them. It's called Yom Kippur. And in fact, starting tonight, those people who celebrate it religiously fast for a day. So I'm going to do that. But my wife isn't. Anyhow. Hi, you are... Wait, I don't want to know until I get rid of this. What did I do here? Wait a second. Let me do this. Let me stop.